In June 2022, northeastern India and Bangladesh experienced one of their harshest floods of the past century. Monsoon season led to torrential flooding that meant streets and houses were underwater, leading to more than 2 million people displaced from their homes. It also means we can't see a full picture of the situation in real time. Monsoon weather like this leads to shutting down airports, making it harder for planes and helicopters to fly. Traditional satellite images are also pretty much useless, obscured by the massive clouds pouring water down. That is until we look at radar satellite imagery. These radar images allow us to see the full extent of events like floods as they're happening, not needing for the storms to settle. Today, I want to show you how these work, why the engineering behind it is so freaking incredible, and why we would even need radar in the first place.
Let's do this as a story, by the way. So this is kind of interesting. This is how I think of it.
This is Darren Muff. He's the director of engineering at ICEYE, one of the companies that builds some of these radar satellites we're going to talk about. I actually used to work there at ICEYE, and this is how I know Darren. He's one of the people that got me excited about this stuff in the first place when I joined there, and he's one of the best people that I know at explaining why this is really cool and how we got there. So Darren's going to do the explanation, but while he does that, I didn't quite know how to animate this part, so I ended up doing it in Lego stop motion, because, hey, why not?
Imagine that you were a World War II hero. You're one of the guys in one of the intelligence community labs doing all sorts of engineering, and somebody comes up to you and goes, you know what, we've got a real problem. We think the Russians are building up a massive army ready for the Cold War. You've got one job, Maxine. You've got to take pictures at night and through cloud. Okay. Now, you know, because you're really good at optics, you know how to take pictures at night. You do this all the time with your mobile phone. You actually have a flash on it. So you want to take a picture at night, you flash the light. It's the seeing through cloud the tricky piece. Our camera can't see through cloud. That's kind of the problem. But we do know that different wavelengths can see through cloud.
To explain this, let me interrupt. I'll show you something that might help. See this graph right there? It shows the amount of attenuation for different wavelengths. And there's a big gap right there between about a centimeter and a few meters. And what we can see here is that these wavelengths don't get absorbed by the atmosphere or the clouds. And that's why we turn to microwaves. They go right through it. So we found which wavelength to use, but how do we make an image from there? You may know that radar is actually an acronym. It stands for Radio Detection and Ranging. Radar is what's called an active sensor. That's the same as the flashlight that Darren was talking about. Light is emitted, in our situation it's microwave light, it bounces off objects and some of it makes its way back to the antenna. We can measure the time it took for the pulse to travel to the object and back and convert that to a distance. We know that the wave travels at the speed of light, which is a constant speed and a known one, so the longer a response takes, the further away an object is. And this is where the first concept of resolution in an image comes in, by the way. As I said, we can measure the distance at which objects are, but there's actually a limit to how close two objects can be together before they look like the same echo to our antenna. That's what's called the range resolution, but we'll touch on that a little bit later. At its most basic, a radar emits a wave in all directions, and we can measure the distance of objects, but we have no idea what direction these are in. This is where the first bit of really clever engineering comes in. In a similar fashion to a camera lens, we can actually focus the pulse to only be emitted in a single narrow direction. Now, any response we get from the antenna means that an object was present, but only within that narrow viewpoint, nowhere else. By the way, spin that around and you've got yourself a radar that can give you an object's direction and distance. And probably also looks quite familiar. Okay, this is great. But we still don't have anything anywhere close to our Bangladesh image yet. To create an image, instead of having a single antenna that's rotating around on a fixed point, we can line up multiple narrow viewpoint antennas next to each other. Each antenna on its own has that narrow field of view, but put together they can cover a much larger area. This is how some of the first operational radar images worked. All the way back in 1983, the Soviet Union launched Cosmos 1500, a satellite capable of producing radar images with a resolution of a whopping 2 kilometers by 1.5. That meant that the smallest features and objects we could individually tell apart in those images had to be 2 kilometers by 1.5 wide. Such a satellite is somewhat useful, but compared to some of the best optical satellites, even back then, that could see less than a meter, it's like comparing the accuracy of a stopwatch to that of a sundial. It's useful, but only up to a certain, very limited point. The resolution of these early radar imaging satellites was limited by a number of factors. I think we've made that quite obvious. For now, let's focus on one we've already touched on a little bit: how narrow those individual beams can be. Well, actually, interestingly enough, the physics that define this angular resolution is the same as for optical cameras. And to explain this a little bit more, let's go back to Darren and to our story.
The equation that defines the angular width of any radiating element is lambda divided by d. So lambda is the wavelength, and d is the diameter of the mirror or the diameter of the antenna. But the engineers had a problem. And here's the problem. The problem is that equation, lambda divided by d, our wavelength has now changed from nanometers to centimeters. A massive scale. If we want to retain the same resolution that we had with our camera, our optical camera, we have to make sure the antenna or the mirror also scales up by the same amount. And that's the problem. The problem then is, how do you take this antenna or mirror for your optical imaging system looking over Russia? It's now got to be many, many kilometers long. How could you possibly do that?
And at first, they didn't. That's why these first radar imaging satellites from the 80s we talked about earlier had such low resolution. The wavelength, lambda, in our equation, now became a lot bigger, but since there's a limit to how large we can physically build an antenna, the resolution inevitably ends up being pretty bad. And it's not just about building a large antenna. At some point, the physics needs to meet the engineering and the logistics. Our antenna needs to physically fit on the top of a rocket, survive all the vibrations of launch, and work on its own in space. Long story short, we need a different approach. Cue to clever bit of engineering number 2. The solution gave its name to how we call these satellites and these images. SAR. It stands for Synthetic Aperture Radar. And by the way, yes, this is an acronym of an acronym. Don't judge the engineers by how they name stuff. Instead of building a giant 100-kilometer antenna, people figured out that you could take a smaller one and record the data it emitted and received along the distance equivalent to this original giant 100-kilometer antenna, making it a virtual or synthetic antenna in a way. We then only processed all these pulses into an image once the satellite covered that whole area of our original large antenna. By the way, this concept of virtual mega antennas created by moving a single one isn't limited to satellites. We can combine multiple smaller antennas into a much larger one, and that's actually how we made those images of black hole in 2019. And this is engineering at its best. We solve what looks like a problem without a practical solution by going back to the first principles of what we're actually trying to do in the first place. Here, we want to make high-resolution images that requires a lot of pulses to be sent towards an object across an impossibly large antenna size. But instead of doing it all at once with a single antenna, we can benefit from the fact that our satellites are orbiting the Earth going at about 7 kilometers per second. And that's per second, not per hour. So now, all of a sudden, 100 kilometers is, quote, just about 15 seconds, recording all these signals and processing them all at once as if it came from a single big antenna. That's why it's called synthetic aperture. Aperture, like in photography, is the size of our lens, or in our case, antenna. We just build it synthetically by combining many small antenna sizes. You can think of this a little bit like how night photographers take long exposure images to capture more light to make these stunning pictures of the Milky Way. The main difference being that where long exposure photography reveals more dim objects, like stars, The more we look with our radars, the higher resolution our images become, the more details we can see. And the craziest part is that this makes the resolution of our images completely independent from how far away the antenna and the objects are. We can make high resolution images no matter how far we are, which comes in really handy when you're trying to put stuff in space. Another tricky aspect of radar is that the pixels in our images aren't necessarily square. Remember the Soviet satellite that I mentioned earlier? I said it took images of 2 kilometers by 1.5. That's what I mean, rectangle pixel sizes. In an optical image, the pixels are square. You can rotate the camera around and the image is still the same. A radar, on the other hand, doesn't necessarily have square pixels. So that means that you could look at the same area, rotate the satellite orbit 90 degrees, take a look at 2 images, and they would be quite different. It's because the parameters defining the resolution in each direction are independent from each other. We touched on this a little bit earlier as well, but let's bring it all together here. There's the range resolution. How close together can 2 objects be for the pulse to still be able to tell them apart? That depends on how short of a pulse we can create. And short pulses require a lot of power, more than can be fit on a solar-powered satellite. And then there's the angular resolution we talked about. How narrow can we make our beams? That's determined by how big of an antenna we could build. I focused mostly on the antenna size, but I want to mention that this is only half of the work. To lower the range resolution below a meter, the trick here was to modulate the frequency of the pulse. By doing so, we can actually tell objects a lot closer together with a lot less power. Taking a step back, we've now built a radar system that gathers a lot of data for a few seconds and processes it all together after the fact. We've effectively decoupled the gathering of the data from processing we do to form an image. This means we can take radar pulses taken from previous satellites and try to make new, better images thanks to new, clever algorithms we've since discovered in ways that weren't possible when the data was collected. The images we make today are, in a way, one interpretation of these physical microwave echoes we gathered, and one that changes over time. In fact, we don't even need to combine all of these signals into a single high-resolution image. We can break our 15 seconds of aggregated data into individual 1-second segments, making individual images out of these to create a short video. If you remember what I said earlier, the longer we look, the higher the resolution of our images, and the inverse is actually true. So if we only look now for 1 second, we'll get lower resolution images, but now we get new information, like the speed of moving objects in the frame of our images, like boats or trains. And this is again why this is so different from optical, and I'd argue also pretty damn cool. Now, this doesn't mean there aren't any trade-offs here. I mentioned that the resolution of our images is independent of how far our antenna is. This is a huge benefit when wanting to put stuff in space. For context, in orbit, our satellites are about 700 kilometers from the ground. Not reducing the resolution of the images that we can take the further away we are seems like it's pretty incredible, and it really is. But while the resolution doesn't suffer, the signal-to-noise ratio does. The simplest way I've found to explain what the signal-to-noise ratio is to look at smartphone cameras. Anyone with a smartphone that has a 100 megapixel camera knows that just because a sensor has high resolution doesn't mean it always takes good pictures, and especially not at night. That's because while there are many individual pixel sensors, each one receives so little light that the data just gets noisy. And a similar thing happens for our radar satellites. The resolution might not change with distance, but the quality of the image degrades. Now, you may be wondering, how far can we push this? And it turns out pretty damn far. We've used radars on Earth to bounce pulses off the moon and back to map its surface down to a resolution of 70 centimeters. And remember, the moon is 385,000 kilometers away. And the best part is, it gets even better. There's a huge element we haven't touched on yet. That makes these already incredibly powerful imaging satellites even more interesting. At the very beginning of this video, I mentioned that radars are active sensors. They create their own signals rather than needing an external source like a camera does. That's a really big difference with how our eyes or regular cameras work. Our eyes need a source of light, the sun or a light bulb, to create light, which bounces off all sorts of different objects until it hits the back of our retina. But these light sources generate a lot of different types of light pulses that are actually pretty chaotic. I mean, the sun is a giant, massive ball of fire after all. But our radar antennas can create very carefully calibrated signals, similar to how a laser could create light at a specific wavelength. This in turn can be leveraged to measure what's called phase. Phase is not a measure of how much a pulse came back or how long it took, but which specific moment in the wave cycle did the pulse get recorded. Measuring phase on its own is pretty useless. It just looks like a bunch of noise. But comparing phase across a set of images allows us to measure differences multiple orders of magnitude more precisely than anything that we've talked about so far. In fact, this principle, called interferometry, is so precise, it's what LIGO used to measure gravitational waves. At its most precise, they could produce measurements down to 1/10,000th of a proton. That's just ridiculously small. In fact, it's the smallest measurement ever attempted by science. Ever. Now, radar satellites can't see things at the scale of atoms, but this same principle, interferometry, allows our satellites to measure and map the deformation of the ground after earthquakes or big explosions like the one in Beirut in 2020, see track marks left by cars as they drive through fields, or, my personal favorite, measure the thermal expansions of buildings. We can look at the physical materials that make up buildings and expanding and dilating due to temperature difference. All of that from freaking space. But radar imaging isn't without its limits, though, and far from it. This may actually be quite obvious by how long it took to get to this point in the video and to just explain how these work. This thing is not intuitive. Our brains have experienced a huge part of the world through our eyes, these squishy little cameras that are plugged into our heads, and are used to interacting with visible light. Images from radars might look like black or white images at first glance, but it's often counterintuitive, and with many artifacts, our brain needs some time and practice getting used to. Let's go back to that Bangladesh flooding image once again. The water in it is black. Well, first of all, water as a material itself reflects microwaves, so most of the pulses emitted by our antenna are reflected, not absorbed, and under calm water, when the surface is flat, most of these pulses just bounce away from our antenna, hence the black image. Nothing came back. If we instead look at images of agitated water, though, some of the pulses bounce back in the direction of the radar antenna and appear as bright areas. Similarly, these nice and tidy buildings and roads with 90-degree angles everywhere that we humans love building are great at reflecting these pulses multiple times, leading to many going back to the antenna and creating these very bright spots. It even sometimes looks like we can see through buildings. But this is simply because, once again, we're seeing a distance measurement. The same wave hits the top of a building and the ground in front of it at the same time, which the antenna then has no way of telling apart. In fact, this example here is so counterintuitive that some of the companies building these radar satellites had to issue press releases, and I kid you not, they had to release press releases that no, they cannot see through walls and into people's homes. Mountains also appear squished to one side. Structures like bridges offer many surfaces microwaves can bounce off of, leading to what appears like duplicates of the same bridge. Moving trains appear to be going completely off track as they change direction during the 15 or so seconds our antenna travels gathering data. To wrap up, SAR is a marvel of modern engineering that allows us to more easily map floods, detect pipeline leaks, measure the impact of earthquakes, and map the world regardless of the weather. In case it wasn't obvious, I find this really fascinating because I also see the story of how we turned to physics to solve a problem we had, not being able to see through clouds, and then had to figure out one by one all the technical problems that came alongside trying to find a solution. And it meant that the solutions that we did end up led us to an imaging system that's harder to interpret and requires some time getting used to. But it's an incredible example of what multiple disciplines, from electrical engineering to rocket science and computer science, can achieve when all put together.
And the one final thing I want to explain, which I think I thought this is cool, but even the noise in SAR is really neat. What you're looking at in the noise, because we're looking in this microwave region, we're actually looking at the cosmic microwave background there. We're actually seeing yeah. So you're in your SAR image, you're looking at the actual, the first initial afterthrows after the Big Bang, like 10 billion years ago in the universe. It's amazing. It's still there in every single SAR image.
Hey, thank you so much for watching this. This is a topic I've been wanting to make a video about for a long time and wanted to take the time to do it justice properly. I want to thank everybody on my Patreon that have been supporting my work. I'll be showing behind the scenes of this video on Patreon, from how we processed and used real satellite images from that Bangladesh flood to all the research that went into making this video. I'm starting to work more with people that are way better at me at specific parts, from Peter, who did the intro music, to Abram, who did the stunning animations, and that costs a lot of money. So if you want to see more of these types of video, the best way to help out is to support me on Patreon. Every little bit helps. I also want to thank Darren for his time, all the people who've helped me write and proofread this script, and specifically I want to say thank you to Jason from Space, who helped fund the creation of this video. Jason and I have actually been friends for quite a while, and he's been a huge advocate behind the scenes for the geospatial industry and just making radar images more accessible to the public. A lot of this video is based on Thomas Ager's Essentials of SAR book. You can see how much I used it there. And they helped translate that book into Mandarin, making it available to a lot more people. They also do professional work training companies looking to integrate radar images into their operations to support new projects. Space provides independent insight on the ground and in space. I hope this video shows that remote sensing, satellite images, and specifically SAR is becoming a bigger tool in just transforming the way we do things, from climate change, agriculture, insurance, and finance. And they help companies integrate with those. I'll have a link in the description if you want to find out more. I've also left a ton of resources and references in the description, but if you want to watch more, I'll have another video right here where I explain what you can generally do with satellite images. And I also have a podcast, and you can listen right here to my interview with Thomas Ager on how he wrote the book and more about radar images. And if you want to see more of these, click on my face where Patreon is. And either way, thank you so much for watching.